feel the vibe.
What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue our work with the FO.1 section, which is Arithmetic and Composition of Functions. Last time we looked at the arithmetic of functions and how that affected domain, and today we are going to focus primarily on function composition. So in order to establish a kind of an understanding of function composition, let's first take a look at some example problems with some techniques that we are used to. So in problem number 5, it says, consider substitution with functions. We're going to find that function composition relies heavily on substitution. Write the output values for each of the following, given that f of x is x squared minus 3. So if we want to find f of 1 means that we need to substitute in this one value, or this value 1, for x. So we would have 1 squared minus 3, and that result would be negative 2. So f of 1 is negative 2. Now in B, in this case, we're substituting in a variable, not a value. But we can still evaluate and go through the process of substitution. So we're replacing x with now a. So f of a would be a squared minus 3, which cannot be simplified. So that would be the end result. In C, now we're going to substitute in another variable. That variable is 2a. So I'm going to take x and replace it with 2a. And 2a squared would be 4a squared minus 3. So this would be the result for f of 2a. So you kind of see this process here. Now let's take a look at D. In D, we're substituting in now more than just a variable, but a binomial expression. So we would substitute in 2x plus 1, again replacing the x with this expression. And so that expression would be squared, and then we would subtract 3. When we square 2x plus 1, we would get 4x squared plus 4x plus 1, and still have minus 3. And so as we simplify, we should get 4x squared plus 4x minus 2. Now we could look at factoring that expression, but this is a good enough expression for the evaluation of f of 2x plus 1. Really, what we just did there in problem 5D was a function composition. We actually did a function composition which would be written as f of g of x, given that f of x equals x squared minus 3, and g of x equals 2x plus 1. So function composition is really just the process of taking one function and substituting it into a different function. So what we essentially did here was we took 2x plus 1 and substituted that into f of x. That is function composition. Now the notation for this could be written as f of g of x. So we say f of g of x, which can also be written in this notation, f of g of x. What it's telling us to do is substitute, again, g, the function for g, into the function for x, for f. So let's take a look at how some more examples may work. In problem number 6, it says, given f of x is equal to the square root of x minus 4, and g of x is 3x plus 2, evaluate each of the following, then determine the domain. So we're going to complete a function composition, and then actually look at the domain. First, let's do the composition. So for A, f of g of x would say to substitute g of x into f of x. So we're taking this expression for g, and we're replacing the input value, x, with 3x plus 2. So f of g of x would be the square root, that is not being changed, of 3x plus 2 minus 4. Essentially 3x plus 2 is within some parentheses, but we generally don't, or in this case we don't need to write these parentheses, as they would not affect the way the problem would be written. So we can simplify this expression slightly here. we can simplify inside the root, inside the radicand, as 3x minus 2. So f of g of x is root 3x minus 2. Now I can find the domain for this. Remember, the domain for a function, a root function, exists where the radicand, or the inside the radical, is greater than or equal to 0 to avoid negative number, or to imaginary numbers. So in this case, I could add 2. So 3x is greater than or equal to 2, and then divide by 3. So my domain would be x is greater than or equal to 2/3. And I could check that domain on the graphing calculator if I wanted to. And we would see that x is greater than or equal to 2/3. So my function composition gives me a root function in this case, and we can find the corresponding domain. Now in B, the notation has changed a little bit. So it's written in the other format, but also the order of the substitution has changed here. This notation in B would be g of f of x, meaning that we are going to now take, meaning that we are now going to take f of x and put it into g of x. So here we had f of g of x goes into f. Here we have g of f of x goes into g. So I'm going to take this expression and put it in there. So I would have 3 times root x minus 4 plus 2. And in this case, there's nothing that I can do to simplify. So I replace the x value, the input value in g of x, with root x minus 4, and there I have my function. The domain for this, again, it's a root function. This root function has some transformations on it, but the domain for this is still going to have to be a radicand that is greater than or equal to 0. So in this case, x would have to be greater than or equal to 4. And we could, again, graph that to see that that domain would match our corresponding function. One more example here. In C, I have g of x. So for g of x here, I'm actually going to take g of x and substitute it back into g of x. This is not always the most common thing, but is valid. So essentially, again, I'm replacing the x value with g of x. So this would be 3 times x, which is now 3x plus 2, and then plus 2 attached at the end. So I'm substituting the function into itself, which I can simplify. 3 distributed through to that binomial would be 9x plus 6. And then we could add the 2 and the 6 together to get 9x plus 8. So g of x would be 9x plus 8. And this is a linear function, so we know that the domain of g of x would be all real numbers. Now in some instances, so previous to this, when we looked at the arithmetic of functions, combining functions through arithmetic, we had rules that allowed us to figure out their domains. For function composition, there are some general concepts that are going to hold true, but there's no real steady, fast rule. What we want to see is the result of the function composition, and then determine the domain based on our new equation. So in the first 2 instances, we had roots, so we had domain restrictions. In the third instance, we had a linear function, which does not have a domain restriction. Let's take a look at some further examples. In problem 7 in your notes, it says, given f of x and g of x from problem 6, evaluate each of the following. So I have listed f of x and g of x here. So in A, I have g of f of 5. So we can go about this in 2 different ways. So you can write this property down if you would like. G of f of A would be the same thing as finding f of A first and then substituting that into, let's say, g of x. So what I could do here for problem number 7 is I can evaluate with f of 5 first, and then substitute that into g of x. Or I can find g of f of x and then evaluate with 5. So we're going to do both examples. So f of 5 would be x minus 4. Now the x is being replaced with a 5. So root 5 minus 4, which would be root 1, which is 1. So f of 5 is 1. So really what I can do here, if I'm trying to find g of f of 5, I can take this number that I know now represents f of 5 and substitute that into g. So this would be the same as g of 1. Or taking the x value in g, so 3x, and replacing it with a 1, which would end up being 5. So g of f of 5 is 5. Now again, this method was by evaluating first f of 5 and then g of that result. I could have first found g of f of x. So I could have taken f of x and substituted that into g of x, which is 3 times root x minus 4 plus 2. And then found g of f of 5 by substituting in 5. So 3 times root 5 minus 4 plus 2. So in this instance, I would have 3 times 1 plus 2, which is 5. So to evaluate a function composition, you can first compose the functions, as I did here with the red example, and then substitute in your value. Or you can substitute in the value into your first function in the composition, taking its result and substituting it into the second function of the composition. So see if you can do B. Go ahead and pause the video and see if you can complete B using a method of your choice. Hopefully you got a chance to do B. B is f of 13. So what I'm going to do first here is I'm going to find f of x. So I'm going to take f of x and substitute it into f of x. So what this would become is the square root of, now x is getting replaced by f of x, which is the square root of x minus 4 minus 4. Now we could simplify this with fraction exponents with rational exponents if we wanted to, but this is good enough to move forward here. If I want to do f of 13, I can take this previous expression and replace the only x value with 13. So what this would give me would be 13 minus 4 within a root, which is 9, and the square root of 9 is 3. So 3 minus 4. And 3 minus 4 is negative 1, and we know that the root of negative 1 is I. So if we wanted to find the exact value, that exact output would be I. Now if you were graphing, this value would be undefined. But for our purposes, I would be the correct solution here as an output to the given input. Now, the other way that you could have done this is you could have evaluated f of 13 first. So you could have just done f of 13. And in this case, you would have the square root of 13 minus 4, which equals 9. Sorry, the square root of 9, which equals 3. Then we could take that 3 and substitute it in there for f of 13. So now you would have f of 3, which is the square root of 3 minus 4, which you can see is the square root of negative 1, which is I. We'd still get to the same result. So really the process is the same. It's just either doing the two steps or the two different operations separately and combining their results, or doing the two different operations together. So function composition can be done either as a composition of the functions first, then substituting the value, or substitution first and then substitution again to match that function composition pattern. Now let's take a look at some graphs. Let's take a look at some graphs in respect to addition and subtraction of functions, or function arithmetic, and function composition. And we're going to use the graphs to evaluate. So this is going to incorporate ideas of arithmetic and function composition. So if I take a look at A, if you remember back to the previous notes video, which if you have not watched, you should pause this video and then go watch that one first. But if I take a look at 8A, I can rewrite the expression f plus g of 2 as f of 2 plus g of 2. And what this will allow me to do is to find output values or evaluate without knowing the exact function rule, or the rule for the exact function that gave us the graph. So we know that f of x is this linear function and g of this x is this quadratic function. We could find their equations, but we don't necessarily need to. If I take my definition for arithmetic of functions, I can do f of 2 plus f of g to evaluate this expression. Now remember, f of 2 is referring to the y-coordinate where x is 2 on the graph. So we're going to assume that these graphs are in increments of 1. And so I would have a point on g of x that is 2, 3. So that means f of 2 is 3. If I go take a look at g of x, I would have a point 2, 4. So that means g of 2 would be the corresponding y value, 4. And so the evaluation of our expression is actually 7. So we're using the graph to find corresponding y values for given x values. Now, for b, if I want to do this function composition, what I have to identify first is what is g of 2. Well, we did already identify that as this point right here. G of 2 would be the corresponding y value when x is 2 on the graph to the right, g of x. So I can replace g of 2 with 4. And now in the process of composition, function composition, I could look for just f of 4. So go to my graph of f of x. I have this point 4, 4. So the corresponding y value where x is 4 would be 4. So f of g of 2 can be evaluated using the graphs without knowing the functions by matching inputs and outputs and substituting them into the expression. Taking a look at C. C is g divided by f of 3, which would be the same as g of 3 divided by f of 3. So we can use the graph to figure out what g of 3 is. G of 3 would be in this location, 3, 3. So the y value when x is 3 on g is 3. G of 3 on f of x is in this location. So we would have 3, 3.5. Which you can simplify. And we can do this in the calculator if we need to. 3 divided by 3.5 will give us a decimal, but we can hit math and then the fraction key. And it'll give us the most reduced fraction. This would be 6 over 7. So g divided by f of 3 is 6 over 7. At this point, go ahead and pause the video and see if you can complete 8D. So in 8D, we're doing a function composition here. We're doing g of 2. So the first thing that we need to identify is what is g of 2. Well, again, that is the corresponding y value. Sorry, I was on the wrong graph there. That is the corresponding y value when x is 2 for g of x. So the y value would be 4. So now we can replace g of 2 with 4 because we can see g of 2 is 4. So what I do now at this point is go back to the graph and look for g of 4, where the x value is 4. The corresponding y value is 0. So the result of g of 2 would be 0. And this is a good place to stop. So here we have seen some examples and definitions of function compositions. And we've also taken a combination of arithmetic and function composition to graphs in order to evaluate expressions. When I see you guys again in class, we'll have the opportunity to go over some questions and get in some additional practice. As always, guys, thank you for tuning in, and I'll see you soon.